Okay. Section 7.5, Properties of Trapezoids and Kites. Our objectives are to use the properties of trapezoids, use the trapezoid mid-segment theorem to find distances, and then use the properties of kites and be able to identify quadrilaterals, so different types of quadrilaterals. Okay, in the last three sections, we were dealing with parallelograms and types of parallelograms. Now we're getting out of parallelograms, but still four-sided figures. So not all quadrilaterals are parallelograms. Some of them are not. And one of them that isn't is a trapezoid. A trapezoid is a quadrilateral, okay, with exactly one pair of parallel sides. Okay. So it only has one pair of parallel sides. Okay, for example, in this figure here, this side and this side are parallel, but these two are not. You can see as they extend out, they will eventually intersect. These two are not parallel, so that makes this a trapezoid. It has to have exactly one pair of parallel sides. Okay, so now we have special names for the pieces of a trapezoid. The parallel sides, in this case, we've got this parallel side. Here's our parallel sides. We refer to those as bases. So a trapezoid actually has two bases. The bases are the parallel sides. The other two sides we refer to as legs. So this side and this side are the legs. So we have a leg here and a leg here. Okay, so we have two bases, two legs, okay, and then we also have what we call some base angles. Okay, the two angles that are on the bases. So if you see here how we have this one angle here, we have this angle, I don't know, let's bring in another color. We have this angle right here and this angle right here. They're both on the same base. They're both on this bottom base here, this longer base. So we refer to those as base angles. This angle right here and this angle right here we refer to as base angles. Okay? But this isn't the only base. So there's actually two pairs of base angles. If I'm referring to this base up here, we can refer to these two. These two angles up here are base angles as well. So this angle up here and this angle here, we can also refer to those as base angles. So a trapezoid actually has two pairs of base angles. Okay, so those base angles come in those pairs there, and it's got two pairs of base angles. Okay. We also have a special type of trapezoid. Again, here's our parallel sides. So here's our two bases. We have this base up here and this base down here. But if the legs are congruent here, this leg is congruent to this leg. If the legs are congruent, we call it an isosceles trapezoid. Has congruent legs. Okay, so if we have a trapezoid with congruent legs, we call that an isosceles trapezoid. So since these two legs are the same, this trapezoid is what we call isosceles. Okay, all right, so here in example one, here we have a quadrilateral 1, 2, 3, four-sided figure in a coordinate plane. We want to show that QRST is a trapezoid, then decide whether it is isosceles. So first, to determine whether it's a trapezoid, this first bit, we need to show we have a set of parallel sides. So I need to, based on this, I'm going to look to see which ones look parallel. Well, RS looks parallel to OT, so I need to find the slope of RS. So the RS slope would be, if I go from R to S, up 1 over 2, so up 1 over 2, and then I need the slope from O to T. The slope from O to T up 2 over 1, 2, 3, 4, up 2 over 4, which simplifies to 1/2. So I know that RS is parallel to OT. And we can tell obviously these two aren't. Okay, but we could also find the slope. This is a vertical. This is not vertical, so I know those two are not parallel. So here we've shown that this quadrilateral is in fact a trapezoid. Okay, now decide whether it's isosceles. So to determine whether it's isosceles, we need to show that the legs are congruent. So if we look at this leg, there's my two legs. There's this one there, that one here. I need to show that they're congruent, that there's the same measure. So to decide whether it's isosceles, I need to show that it has congruent legs. So to do that, I'm going to find the length of each of these legs. So I need to find the distance. So this is going to be using the distance formula. Okay. I would need to it's x2 minus x1 squared, y2 minus y1 squared. Okay, so I'm going to have to find the distance from O to R. That one's vertical, so I can just count 1, 2, 3. So the distance from O to R is 3. So again, OR with no symbol above it is talking distance. Now I need the distance from, I did O to R, now I need S to T, the distance from T to S. That one's not vertical, so I'm going to have to use the distance formula here. Okay, so we'd have 2 minus 4 squared plus 4 minus 2 squared. Okay, so we have 2 minus 4 squared. I'm going to do all of that here in my calculator, shorten things up. 2 minus 4 squared plus 4 minus 2 squared gets me 8. Okay, so this would be the square root of 8. Is the square root of 8 the same as 3? Nope. So this, since OR does not equal ST, it is not isosceles. Okay, it is not isosceles since those two sides aren't the same. And at first glance, it looked like they are, and they're pretty close. The square root of 8 is 2.82. That's pretty close to the 3 that we got for the other side, but not exactly, so it's not exactly isosceles. So always make sure you check those distances before you just look at it and assume. Okay, so now that we know what a trapezoid is, and we know about the parts of a trapezoid, let's look at some of its properties. Okay, so first we have the isosceles trapezoid base angles theorem. If a trapezoid is isosceles, so we start with an isosceles trapezoid, so there's our hypothesis. So if I know this is an isosceles trapezoid, meaning parallel lines, legs congruent, then each pair of base angles is congruent. Okay, so let's go ahead and label these points A, B, C, D, so we can talk about them. Okay, so since we know these two are parallel, which makes it a trapezoid, these two are congruent, which makes it an isosceles trapezoid, then we know the base angles are congruent, meaning I know if we look at our bases, my base would be here, and there are my two bases. So here we have base here, base here. Each pair of base angles is congruent, which means the angles at this base, angle A and angle D, are congruent. And the angles at this other base, angle B, congruent to angle C. It doesn't mean all 4 angles are congruent. It means these two ones on this base are congruent, these two ones on this base are congruent. Okay, and we know since this is a 4-sided figure, if we remember from previous quadrilateral, all the angles have to add up to 360. Okay, that was from, I don't know, a couple sections ago. Okay, so here's the isosceles trapezoid base angles converse. If a trapezoid has a pair of congruent base angles, meaning if I start by knowing, first of all, I start by knowing it's a trapezoid, meaning parallel and parallel, so I have my two bases, base and base. Again, let's go ahead, let's label these points A, B, C, D. Here's if I know these base angles are congruent, meaning if angle A is congruent to angle D and angle B congruent to angle C, then I know it's isosceles. And if it's isosceles, then I know AB, segment AB would be congruent to AB would be congruent to DC. Then I know the two sides are congruent. So here it starts by, if I know the legs are congruent, then I know the base angles are. Here it's the other way around. If I know the base angles are congruent, then I know the legs are. Okay, again, it's just that converse idea. Okay, and now we have the isosceles trapezoid diagonals theorem. If a trapezoid is isosceles if and only if, which means this is a biconditional, it goes both ways, meaning we could go from here to here, or we could go from here to here. If it is isosceles, then its diagonals are congruent. So if I draw these diagonals in, if we draw this diagonal in, and then this diagonal in, let's label our points again so we can talk about them, A, B, C, D. So if a trapezoid is isosceles, then its diagonals are congruent. So that means A to C would be congruent to B to D. And if I have a trapezoid and its diagonals are congruent, then it's isosceles. So it goes the other way around. Okay. So here, example 2. ABCD is an isosceles trapezoid. So we start out by knowing it's isosceles and trapezoid. The measure of angle A is 42. Find the measure of angle B, C, and D. Well, I'm going to come in and I'm going to first mark my bases. There's a base, there's a base. So since A is 42 and it's on this base, the other angle on this base will also be 42. So I know the measure of angle D here is also 42. Okay. So I know the measure of angle D is 42, but I don't know these two angles. But since I know it's isosceles, I know whatever they are, they're going to be the same. So this angle is going to be congruent to this one. But I don't know what they are. So since I don't know what they are, but I know they're the same thing, I'm going to use the variable. Let's say this angle's x and this one's x. So both of these two angles are the same thing. This is a quadrilateral, which tells me the angle sum is 360. So I know if I add up all four of these angles, I get 360. So let's add them up. X plus 42 plus 42 has to equal 360. X and x is 2x. 42 and 42 is 84. Has to equal 360. So we're going to subtract the 84 from both sides. So 2x equals 360 minus 84, which is 276. And then divide both sides by 2. X then equals 276 divided by 2, 138. That tells me each of these angles, x, would be 138 degrees. Now, okay, these two base angles are equal. These two base angles are equal. When you add them all up, you get 360. Okay. So the measure of angle B is 138. The measure of angle C is 138. And the measure of angle D is 42 degrees. So we found the measure of angle B, angle C, and angle D. Okay. Next, a mid-segment of a trapezoid. Okay, just like we had the mid-segment of a triangle, we have a mid-segment of a trapezoid. The mid-segment of a trapezoid is the segment, is this of course a segment, okay, whose endpoints, let's change the wording on that, whose endpoints are the midpoints of the legs. Okay, so if I was to draw in this midpoint, okay, so congruent, congruent, draw in this midpoint, congruent, congruent, and connect them, I will have drawn in a mid-segment. So there is my mid-segment. My mid-segment is this guy right here, because it goes through the midpoints of each leg. Okay. So now we actually have a trapezoid mid-segment theorem. okay, because there's some interesting things about this mid-segment. First of all, the mid-segment of a trapezoid is parallel to each base. So, since the two bases are parallel, this mid-segment is parallel to them. So I end up getting 3 parallel lines. Parallel, parallel, parallel. Okay? And its length, this length of this mid-segment is half, 1/2, the sum of the lengths of the bases. Okay, so let's give some points to this. Let's call this trapezoid A, B, C, D. And let's call this mid-segment M to N, is these points. Okay, so first of all, MN is going to be parallel to AB. So we know AB is parallel to DC, but it's also parallel to MN, that mid-segment right there. So all 3 of these pieces are parallel. And also what's interesting is the length of this mid-segment, the distance from M to N. This distance from M to N is equal to 1/2 times the sum, that's adding the other 2 pieces. So if I add the other 2 bases, so AB plus DC. Or I always like to think of it as it's equal to the average of the bases. Okay, I always say the mid-segment is the average of the 2 bases. Okay. Okay, so if I was to average, and again, average is add them and divide by however many there are. So if I add these 2 and divide by 2, which is the same as adding these 2 and multiplying by 1/2, okay, it gives me what the length of this mid-segment is, which is kind of cool. Okay, and that's true of any trapezoid, not just isosceles. Like here, I have a trapezoid, obviously not isosceles. This side looks way shorter than this one. Okay, so in the diagram, MN is the mid-segment. We want to find the distance from M to N. So that's what this means. This is talking about the length or distance of MN. Well, I know that MN is going to be equal to the average of the other 2 sides. So PQ plus SR, that's an R down there, divided by 2, the average of them. So, or the same as AB. So this is the same as writing up here. Let's write it the other way. AB plus DC divided by 2, meaning the same thing. This and this, same thing. Okay, so PQ plus SR divided by 2. Well, PQ is 12. SR is 28 divided by 2. So if I take 12 plus 28, so MN, 12 plus 28, 20, 30, 40, divided by 2, 4 divided by 2 is 20. So the length of this is 20. And if you notice, it's 8 away. If I add 12 plus 8, I get 20. 20 plus 8 is 28. So the difference between these two, this is 8 less, this is 8 more. Okay, and that's kind of how averages work. Okay, it'll be the same distance from both. Okay, so if we look at the 12, 20, and 28, 12 plus 8 is 20, 20 plus 8 is 28. Okay, so it kind of has that bit of a, you add 8 to get between the two. Okay, now example 4. Find the length of the mid-segment of YS, YZ, Find the length of the mid-segment YS and trapezoid STUV. I think this is supposed to be an S right here, or this is supposed to be a Z. We're looking for the distance of YZ, okay, in this trapezoid. Okay, so for me to find the distance from YZ, I need to take the average of the bases. So if this is my mid-segment, that tells me these 2 things are the bases. So YZ is going to be equal to the distance from S to V plus T to U divided by 2. So I need to find what SV is, and I need to find what TU is. Okay, because they don't give me that. I'm going to have to use the distance formula there. Again, the distance formula. X sub 2 minus X sub 1 squared plus Y sub 2 minus Y sub 1 squared. Okay, so I'm going to have to find the distance from S to V first. So let's find S to V, the square root of. So we're going from S to V. So 0 minus 2 squared plus 6 minus 2 squared. So again, I'm going to use a calculator to help eliminate any error. 0 minus 2 squared plus 6 minus 2 squared gives me 20. So SV is the square root of 20. Okay, and then TU, the square root of T8 minus 12 squared plus 10 minus 2 squared is the square root of 80. Okay, so now I'm going to simplify these so I can get a little more of an exact answer. The square root of 20, I can break that up into the square root of 20 is the same as 20 is 4 times 5. Oh. Okay. And I can take, that would be the square root of 4 times the square root of 5. The square root of 4 is 2 times the square root of 5. So the square root of 20 is the same as 2 the square root of 5. I can do the same thing here with the square root of 80. Okay, what multiplies to give me 80 in my perfect squares? I'm going to try, we could use 4 and 20, but I think we can go bigger. 9 won't work, so maybe 16. 16 and 5. So that would be the square root of 16 times the square root of 5. These are Algebra 1 skills, so if these confuse you, please come see me. Square root of 16 is 4, so we have 4 times the square root of 5. So for me to find y to z, I need to take SV, which is 2 square root of 5, add it to TU, which is 4 the square root of 5. So to find yz, I'm going to take SV, which is 2 square root of 5, add that to 4 square root of 5, and then divide that by 2. 2 square root of 5 plus 4 square roots of 5. I have 2 root 5s, I have 4 root 5s, so I have 6 root 5s total. Then I want to divide that by 2. So if I take 6 root 5 and divide it into 2 groups, I'll have 3 root 5 each. So this tells me that yz is equal to 3 the square root of 5. Exactly. I get the exact measurement for yz. Okay. All right. Last figure we have to talk about is a kite. Okay, we're going to talk about these very briefly. Okay, a kite is a figure just like you think it would. Okay, a kite looks like a kite. It's a quadrilateral. Okay, that has 2 pairs of consecutive congruent sides. Meaning the congruent sides aren't opposite each other, they're side by side. So here's one set of congruent sides. Again, do you notice here they're side by side? And then we have another set of congruent sides. That would be these ones over here. Again, they're side by side. So we have 2 sets of congruent sides, but they just happen to be connected instead of across from each other. And that makes a kite. Okay? We have a couple kite theorems. We have our kite diagonals theorem. If I draw in the diagonals of a kite, so connecting opposite vertices, if I draw in this diagonal, and then we draw in the other diagonal, what's interesting about kites, all kites, is that the diagonals are perpendicular. So we know they're going to make a 90-degree. The diagonals are definitely not congruent. You can tell this pink one's way smaller than this green one. But we do know that they make a 90-degree angle. So if I have a kite, their diagonals are going to be perpendicular. Okay. Another thing is the angles of a kite. If a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. Meaning there's only one pair of opposite angles that are congruent. And how you find those opposite angles are congruent is if you notice these 2 are my congruent sides, and these 2 are my congruent sides. Where the non-congruent sides meet, here let's label these points A, B, C, D. Where the non-congruent sides meet are the congruent angles, meaning this angle here, angle B, would be congruent to angle D, but angle A is not congruent to angle C because it has exactly one pair of opposite angles congruent. Exactly one pair, meaning not all opposite angles are congruent. just the ones where the non-congruent sides meet. So where the green and the pink meet, and the green and the pink meet, those are our opposite angles that are congruent. Okay, so here it says in example 5, find the measure of angle D in the kite shown, so angle D. Well, if we go ahead and highlight congruent sides, this side's congruent to this one, and this side's congruent to this one. Okay, so here we have where the pink meets the green has to be congruent. So we know angle D is congruent to angle F. So whatever angle measure this is, if we use an X for this angle measure, this one over here is also going to have to be an X. And since it's a quadrilateral, all four of the angles have to add up to 360. So if I add up all four of the angles, X plus 115 plus X plus 73, we get 360. So if we add those, we'd have 2x plus, we go 115 plus 73, we get 188. Subtract the 188 from both sides. $172. Divide both sides by the 2. X would be equal to 86 degrees. So that tells me the measure of angle D is 86 degrees. But also the measure of angle F is also 86 degrees. Okay. All right. I know this video has gone long enough, but I just want to talk a little bit about how these all fit together. Okay. So if we think of this as all quadrilaterals are in this group here. Okay. Some of these quadrilaterals have opposite sides parallel. We would refer to them as parallelograms. Some parallelograms have 90-degree angles. We call those rectangles. Some parallelograms have congruent sides. We call those a rhombus. Okay, so a rectangle is a parallelogram with 90-degree angles. So if we mark those. Whereas a rhombus is a parallelogram with congruent sides. Okay. If my parallelogram has both, we call it a square. Okay. So all squares are rhombuses, all squares are rectangles. Okay. Some rectangles are also rhombuses if they're a square, right? But all rectangles are parallelograms, all rhombuses are parallelograms, and all parallelograms are quadrilaterals. But some quadrilaterals don't fit in this parallelogram group. Instead, they're in the trapezoid group because they have one pair of parallel sides. And then if the legs are congruent, we call them isosceles. Okay. And then we have some quadrilaterals we refer to as kites. Okay, and that's if the consecutive sides are congruent. Okay. But there are some quadrilaterals that don't fit in any of these categories, okay? Like this one here. Nothing parallel, okay? Or this guy, oh, that guy's probably a kite. Okay. There are some that don't fit, okay, that's not a parallelogram, that's not a trapezoid, that's not a kite, and that's okay. Okay. So if you're having a hard time with this vocabulary, please come see me. I'll try to explain it in another way. Okay. Make sure you jot down your practice. Good luck.